Welcome to Analog Electronics. Today is the 33rd lecture and we are going to talk about op amp design along with compensation. So, this is going to be kind of an example of a summarization of all the stuff that we have learnt so far. Okay. So, pretty much the culmination of all of the things that we have learnt, right. We started with the objective of being able to design an op amp, and today we are going to give a demonstration of that. Okay. So, first, if you are planning to make an op amp, then you need DC gain, right. Your objectives are DC gain. You have a second objective, and that is bandwidth. Okay, these are your primary objectives. Your constraints are of course power consumption, right. This is one of the important constraints. The other, there is one more important constraint which you have not seen so far, and that is area or size. Okay, especially when we are talking about electronic circuits that will go on an integrated circuit. The size of the devices matters, because size is directly proportional to how expensive the circuit is going to be. So, you want to make things cheap. One of the goals of engineering is to make your electronics cheaper, right. So, in that sense you need to be able to conserve on the size. Okay. Size directly relates to the size of the capacitor. Capacitor is A epsilon by D, right. So, size of the capacitor, sizes of the individual devices. So, all of these finally relate to size. We are not really going to focus that much on area and size right now, but this is usually one of the constraints. So, if you are employed in the industry, then you will find that area is something that people are worried about all the time. Fine. So, we are planning to make our op amp, and there are two constraints, important objectives. One is DC gain, the other is bandwidth, and we have a constraint on power consumption. All right. What is going to be the structure of our op amp? You probably will have, let us take one of the simplest cases. It is going to start with a differential pair. This is the input structure, a differential pair, and usually when you have a differential pair, you will have to have a tail current source. Okay. The differential pair will have to drive a load as well, and this load is typically going to be made up of PMOSs, not resistors. All right. And supposing you are thinking of a single output differential input, single ended output op amp, then this load could also be, in the most simple case, in one of the simpler cases, it could be an active current mirror, right, self biased active load current amplifier, differential amplifier. Okay. We could have something like this in one of the simpler situations. In this case, the output of this amplifier comes out of this particular node, and typically you are not going to get enough gain. Suppose your gain requirement is 1000, all right. You are not going to get enough gain, you are not going to get 1000 DC gain from the first stage itself. The first stage will probably give you a differential gain of 40, okay, in which case you need yet another stage of amplification. Now, the second stage of amplification, if the first stage is giving you a single ended output, right. The second stage of amplification does not have to be differential anymore, all right. So, in such a scenario you could have either just one common source amplifier, or you could even have a common source amplifier with a common source amplifier as a load. So, one popular structure is something like this. Okay. The NMOS common source amplifier has a load which is a PMOS common source amplifier, right. The PMOS common source amplifier has a load which is an NMOS common source amplifier. All right, this actually works quite well. This is called the CMOS inverter. This is actually a very popular digital circuit, the CMOS inverter, NOT gate. Okay, the NOT gate also happens to be a common source amplifier, right. PMOS common source amplifier, NMOS also is a common source amplifier. Okay. So, this is the structure. We have one loose end over here. This particular node is not really biased, right. This needs to be biased out of some constant GM biasing circuit. Okay. Typically that is how it is going to be done. You are going to make a constant GM biasing circuit. What does that look like? Something like this. Okay. There are more sophisticated constant GM biasing circuits as well, right. You could even have cascade current mirrors, all kinds of sophistications could be brought into this constant GM biasing circuit, depending on how constant you need the GM to be. All right, something like this, right. You will have some ratios of these W by L's. Okay. Remember to check this circuit once more for your own benefit, right. This is actually a very useful small little circuit, and the result is going to be, the result of this is going to be that the GM of these two devices is going to be related proportional to 1 by R. Okay. It is going to be related to R and the value n, okay, 1 by R and something to do with n. Okay. I think square root of 1 by n minus 1 or something, I have forgotten what it is, or 1 minus 1 by n, something like that. It does not matter, it is a constant number, right, which is related to n and R, 1 by R. So, the GM of the input differential pair is suddenly proportional to 1 by R. So, that is the magic of this. All right, this is now my overall structure. Okay. Now, supposing, let us throw in some numbers over here. So, let us say GM of all the NMOS devices after doing this constant GM biasing circuit, let us say GM of all the NMOS devices is 0.1 millisiemens, all right, and RO of all the NMOS devices, suppose it is or rather GO GDS, suppose that is equal to 1 microsiemens, fine. and at the same time for the same size of the MOSFET, suppose the PMOS will have a GM and correspondingly GDS is 0.5 microsiemens, okay, for the same size of the NMOS. Typically what is going to happen is that you want to keep these two of similar order of magnitude, not really necessary, but you can do that. Okay. For example, over here it is not really required, whereas over here it is going to be required, okay, because this is a CMOS inverter. You want the GMs to be equal, the GDSs to be equal, all right, otherwise it is going to be suboptimal. The behavior of this second circuit is not going to be optimal. All right. So, this is kind of the structure. I am just trying to motivate an example op amp over here. This might not be the op amp that you finally end up with, but this is just trying to motivate an example op amp. Okay. Now, how are we going to proceed? What is where is bandwidth coming in? Number 1. So, what about DC gain? As far as the differential mode is concerned, right, from what you I hope remember is that this first stage, in this first stage this node will somehow act like a virtual ground, not really virtual ground, but somehow it so happens that this acts like a virtual ground and double the current comes out over here. Okay. The way it works is that this node does not move, right. If this is V in minus, this is V in plus, the middle node does not move at all. Okay. GM times V in plus current comes this way, all right. This current is reflected over here by the current mirror. So, the top PMOS is actually pushing a current GM times V in plus, fine. On the other hand, this NMOS is pulling a current GM times V in minus, which means that the current that is pushed out is GM times V in plus minus V in minus. But a current can't go into a gate, okay. You are pushing out a current, it is trying to go into two gates, this just does not happen, right. The gates do not draw any current. So, it is going to respond by increasing the voltage over there, right. How is the current going to get converted into voltage? It is going to get converted into voltage with the help of the output impedance at that particular node. So, at that particular node, at this node, the output impedance is the impedance of the PMOS in shunt with the impedance of the NMOS. So, effectively the voltage over here is going to be GM times V in plus minus V in minus times RO of the RDS of the PMOS in parallel with RDS of the NMOS. I am assuming once again that this node is not really moving, this is like a ground. Okay. So, this is how you analyze this circuit very fast. So, instead of a current being pushed out, now the voltage over here rises by a value GM times V in plus minus V in minus times the current, which is RDS P in shunt with RDS N. All right. And then what happens in the next stage? This is the first stage. First stage is done. In the second stage, I have a voltage which has gone up, right. The NMOS responds by drawing a current. Okay. How much current is it going to draw? It is going to draw Gm of NMOS times the voltage that has gone up. The PMOS also responds by drawing a current, Gm of PMOS times the voltage that has gone up, small signal incremental voltage that has gone up. Net, you have a current coming in from outside, which is Gm of NMOS plus Gm of PMOS times the amount of voltage that has gone up. All right. Now, again this is an empty node, current can't really be drawn. So, therefore, this is going to be multiplied by the output impedance of the circuit, which happens to be RDS of PMOS in parallel with RDS of NMOS. Net result is going to be this, that my DC gain is going to be Gm of NMOS times RDS P parallel RDS N. This is in the first stage, and in the second stage I have Gm of NMOS plus Gm of PMOS times RDS of P in parallel with RDS of N. Okay, 1 and 2 relate to first stage and second stage. Okay. Now, if these are all equal, then you can combine them. If they are not equal, then you calculate and figure it out accordingly. Okay. It is unlikely that they will be equal. Gm of the second stage is uncontrolled in this particular circuit. It has nothing to do with the bias current, okay, for example. So, you can't really combine the two, but anyway, this is how you figure out the overall gain. Okay. Suppose Gm is equal for everything, then I have got 0.1 over here, 0.1 plus another 0.1. So, 0.1 times 0.2, right, and RDSP in parallel with RDSN is RDS N is 1 mega ohm. So, RDSP is also going to be 1 mega ohm. So, this is 500 kilo ohms, this is also 500 kilo ohms, right. So, I have got 0.1 millisiemens times 500 kilo ohm will give me a gain of 50, and then I have got 0.2 and 500 kilo ohms, that will give me a gain of 100. So, 50 times 100 something like 5000 is what you have computed over here, okay, with these numbers, with the numbers that I have given you, assuming they are all equal. Okay. Now, let us say you have got this gain of 5000, then you say that all right, now I need to make sure that my phase margin is 60 degrees. How are you going to do that? So, what is, how will you work out the phase margin? So, let us simplify the circuit and redraw this circuit, this differential circuit with first stage, second stage. Let us simplify it and redraw. So, after simplifying and redrawing, basically what am I going to do? I am going to assume that this node is at some ground, right. I am going to throw in all of this, and let us just draw half of it. okay, something like this. This is a current mirror, V in plus is being mirrored, sorry, this G m times V in plus current is going to be mirrored, otherwise I just keep everything. And then I have replaced the PMOS, RDS P and RDS N I have replaced with this rectangle, and I have combined GMN and GMP inside this. Okay. And we have to work out the individual capacitances. So, for example, this particular MOSFET has both the PMOS as well as the NMOS inside it. All right. So, when we talk about this capacitance, this should be the sum of C gate to drain of the PMOS and C gate to drain of the NMOS. Okay. Then there is going to be some capacitance over here, that is going to be C drain to body of PMOS plus C drain to body of NMOS, right. Then source to gate to source capacitances will come over here, right. This is the second stage is done. Now, the first stage. In the first stage, I have drain to body capacitance of the PMOS as well as of the NMOS, right. Those capacitances come onto this node. Fine. Then what else do I have? I have drain to body of the PMOS, I have drain to gate of the PMOS as well. Okay. I have drain to gate, I have source to body which is irrelevant, and I have gate to source. Something like this. Okay. Then for the NMOS, we have gate to source, we have gate to drain, we have source to body which is irrelevant, assuming this is at ground already, and drain to body we have already accounted for. Similarly, we have capacitance for the other NMOS, and for the top corner PMOS we have capacitances, gate to source which adds on to this, we have gate to drain which is shorted out, we have drain to body which gets added on to this, right, and source to body which is shorted out. So, nothing extra. Okay. Some things get added on onto this particular node. Fine. So, this is how it is. This is the overall structure. All right. Now, one possibility is that we just figure out we need to somehow simplify this whole thing, right. It is possible to simplify it, all right. If we can just do something like this, we can say that let us forget about that entire structure. All that we are going to think of is 2 GM, I am sorry, uh, something that looks like this, V in plus minus V in minus and GM times that current is pushed in. Okay. Remember, this current was GM times V in plus minus V in minus. Okay. So, you can model this entire thing as just one device with a GM, all right, and then you need some output impedance over there, right, the corresponding output impedance of that node and the corresponding capacitance, output capacitance of that node, and you need some capacitance over here and some capacitance over here. These can be worked out. Okay. I am not planning to work those out right away, but can be worked out. So, you are going to model this entire network by the way, all of this is nothing at DC, at small signal increment. In the small signal incremental picture, this is a ground, because this does not change with signal, right. None of the currents voltages here change with signal. So, therefore, this voltage is fixed with signal, which means that this is ground in the small signal. If this is ground in the small signal, then this device behaves like a resistor in the small signal. Okay. So, this entire thing is going to be modeled as this one device, right. How can you do such a thing? By just estimating the output current, the output transconductance, short circuit output transconductance, and by estimating the output impedance. So, this is like a gigantic Norton equivalent of the entire first stage. Okay, that is the plan. Now, once that is done, the second stage I have already modeled, right. This capacitance has to be combined with the other one. Okay. And now, it looks like my two stage cascaded amplifier, and the two stage cascaded amplifier we have just learnt how to compensate. How do we compensate the two stage cascaded amplifier? By adding extra capacitance between these two nodes, right. There already was some capacitance, we need to add on to it. Okay. How do we need to add, how do we figure out how much to add on? We can figure out by estimating the first pole with the Miller amplified second capacitor. We can figure out the second pole by assuming that these capacitors are short circuits at the very high frequency that we are talking about. Okay. So, this looks like a diode connected transistor. So, we figure out the first pole and the second pole. The ratio of these two poles has to be as specified by the phase margin and the DC gain. So, DC gain and phase margin, we already know the ratio of these two poles, right, and that will give us how much this extra capacitance has to be. Fine. Now, this is the methodology. I am just trying to go through the entire methodology. After doing all this, you should be telling me that we made one mistake. Okay, what is the mistake? The mistake is that so far we have not talked about, we have seen that the output impedance has two poles, right. We have been talking only about those two poles. The short circuit transconductance gave us a couple of right half plane zeros. One of those two right half plane zeros is at a very large frequency, this input right half plane zero, right. This is at a very large frequency because GM is going to be large and this overlap capacitance CGD is going to be small. So, this particular one is not really of any concern. However, we have added on to this capacitor value, right. We have increased this capacitor value. It is no longer just a parasitic overlap capacitance, it is no longer gate to drain capacitance. Okay. We have added, by doing the compensation exercise, we have added extra stuff over here, right, and that is going to make this second right half plane 0, the location of the second right half plane 0, if you remember. If you do not remember, we will work it out again, right, how to quickly estimate the right half plane 0. There is a nice shortcut method, but in any case, if you remember, it is GM of the second stage divided by this capacitance, all right. Now, this capacitance has become large and therefore, this particular frequency has become a reasonably small frequency, small enough to start competing with the two poles. It might even come in between the two poles and it is going to mess up your entire plot, Bode plot, right. All the phase margin calculations, everything is going to go for a toss, because now there is a right half plane 0. Remember, we did the phase margin calculation assuming that the system has only two poles, we did not talk about any zeros, right, and for that phase margin calculation we found that there needs to be a certain ratio between the two poles. Now, if you throw in a 0, the entire thing is out. Okay. So, we somehow have to do something about this particular 0. So, let us do a quick thing. Let us see, let us just do one analysis. Oh, this was called C23. Okay. So, this is my second stage, all right, and suppose I ask you to compute only the 0. Okay. Suppose I ask you to compute only the 0. Is there any intuitive way to find out, to calculate this 0 without going into complex calculations? And the answer is yes, there is, right. What you have to first figure out, realize, is that a 0, the meaning of a 0 is that the response at that particular frequency is equal to 0, which means if I apply a voltage at the input, then at that 0 frequency the output is going to be 0. Okay. This is the meaning of the word 0. However, you also have to understand that this frequency that we are talking about is not really any frequency. Okay. On the S plane, this frequency happens to be on the real axis, it is a right half plane 0. So, it is going to be over here, okay. And this is not really a so called frequency, right, it is some sigma, it is not omega, right, which means that the kind of input you have to apply is not a sine wave, right, you have to apply some kind of e power sigma t, right. So, if I apply a voltage over here looking like e power sigma t, then the response is going to be 0. Okay. This is the understanding, fine, all right. Now, let us just apply that input, whatever that input is, let us apply that. Okay. It is probably e power sigma z times t, let us apply that. Now, after I have applied that, the voltage over here is 0, which means that the current through these R 3, C 3, all of that is equal to 0. Okay. So, both sides of R 3 and C 3, the current is 0. The current through R d s, remember inside the MOSFET there is R d s to ground. The current through R d s is also 0, because both sides are at 0 volts. So, it does not matter. So, all that is there in the MOSFET is G m times V in. Okay. And where is this current going to come from? All the other currents are 0, it has to come through the capacitor, there is no other exit way for it, all right. So, if you do a quick KCL, now you have got G m times V in is equal to V in times C 23 dV by dt. And that is going to be sigma z V in dV in by dt is sigma z times V in. Right. Is this okay? And that means you can now cancel V in from both sides, and suddenly sigma z is equal to G m by C 23, nothing else. It is not dependent on any other parameters, all that it depends on is G m and C 23. Fine. Is this analysis okay? All right. Now, supposing this was not a pure capacitor, we could just a minute, we could also have, instead of doing this time domain calculation, we could also have written it as V in times S C 23, where S is implied to be equal to sigma z. Okay. So, instead of doing this time domain calculation, we could have done G m times V in is equal to, right, this is the Laplace transform, capital V in is equal to V in times S C 23 at S is equal to sigma z. Fine, we could have done that. All right. Now, suppose this capacitor is not a capacitor, but an impedance Z. A complex impedance Z. Then what will you do? You are going to do G m times V in is equal to V in by Z at S is equal to S Z. You have to work out what Z is at S is equal to S Z, sigma Z. Okay. So, suppose this Z is a capacitor in series with a resistor. C23 in series with R23. Suppose, then what's going to happen? You are going to say GM V in is equal to V in times V in by GM V in is this current is equal to V in by the series combination of this R23 plus 1 by sigma Z C23. Is this okay? And in such a case, you can still cancel V in from both sides, and then you can simplify. Fine. Okay. So, I have just simplified it. If and whenever you do such a thing, you have to do a sanity check. If R23 happens to be 0, the way I have written it, you automatically see that the answer is the old answer GM by C23. Okay. But this also gives you a new result, that if R23 happens to be equal to 1 by GM, then what happens? Sigma Z is infinite, right. So, sigma Z, the 0 frequency, is thrown off all the way to infinity, right. So, it is now a 0 at infinity, which is as good as saying there is no 0 anymore, right. There is no such 0 frequency anymore. So, all that you have to do now is have R23 in series with C23. Okay. So, therefore, the plan is that instead of compensating with just a capacitor C23 between these two nodes, we are going to compensate with this structure, where this resistance is 1 by the sum of these two GMs, right, and this compensation capacitor is whatever compensation capacitor we had calculated. Okay. So, this is how you compensate the overall circuit, right. This is kind of the final result of compensation. Fine. So, what all have we learnt? We figured out how to do find out the 0 frequency in a short way, right. What is the short technique? The short technique is to assume that at that 0 frequency the output voltage is equal to 0 by definition. Okay. Then all of these extra things go away, all that remains is G m and whatever is happening in the cross path, right, and from that you can work out the 0 frequency. Fine. This is one thing. We also figured out how our overall compensation technique is related to our op amp design, right. We took an example of a complicated, this is actually not a simple example. This self biased active load op amp, right, diff amp, is actually one of the more complicated ones. If you think of an ordinary differential amplifier which is completely symmetric, then the result is even easier, because you just break it up into half circuits and in the half circuit you do the compensation, right. You do the you draw your complete amplifier, break it up into half circuits. In the differential mode half circuit, you apply your compensation technique, do the compensation in the differential mode half circuit, and then reverse, come back to the full circuit, right. In the full circuit you will have two compensation capacitors across the two output stages, right, in the two halves. So, that is the more general technique of doing this. So, all the things that we have studied, current mirrors, right, differential amplifiers, constant GM bias circuits, right, and then all of these frequency response things, they all come together and finally you make the op amp. So, op amp design is something that puts all of these techniques together. Okay. So, invariably in exams of this particular course, you are going to get an op amp design, right. Either you will be asked, you will be given some, I mean typical questions can be in two different ways. One way is that you are given the specs like DC gain. Oh, we did not talk about bandwidth. Okay. So, we have to talk about bandwidth. We are going to talk about bandwidth just now. So, you are going to typically questions are going to be, you are going to be given DC gain, bandwidth, power consumption, and then you will be asked to design the op amp, right. One can walk through these steps. The other possibility would be to analyze, right. You will be given the op amp circuit and you will be told that okay, tell me what is the DC gain, tell me how do I compensate this, what is that compensation capacitor, right, and then what is the bandwidth, what is the power consumption. So, at the undergraduate level we normally avoid design type questions, we ask analysis type questions. However, design type questions are more useful, right. That kind of an exercise gives you a direct insight into how the op amp is going to be designed in the industry, right. So, engineering, a lot of engineering is preparing you for the industry, not preparing you for exams, right. So, if you want exam preparation, then yes, at the undergraduate level this is what we ask you to analyze, not design, but in the industry you will be asked to design an op amp. Then what do? Do you say I did not study design, I studied only analysis? No, you have to buckle up and you have to design to the specifications that have been given. Okay. So, these are the two kinds of exercises that you normally get, design and analysis. All right. Now, quickly we are going to talk about bandwidth. Bandwidth is actually very straightforward. Remember when we did the Bode plot, we had two poles, right. We had a DC gain and then we had 2 poles. And for a given phase margin, we also had a relationship between the 2 poles, right. We had omega 2 by omega 1 equal to so much, right. We also had a second relationship and a simpler one between omega 2, omega 1 and omega naught. Okay. Omega naught is the gain crossover frequency, that is the frequency at which the gain is 0 dB, or in other words 1, the gain is 1 at this particular frequency. Okay. So, we had a relationship between omega 2, omega 1 and omega naught, and that was typically something like omega naught squared. If you can check your notes, one plus a naught cos phi. Yeah, something like this. Okay. So, if I know the value of omega 1, omega 2, then I know the value of omega naught. If I say, just look at the Bode plot, if you say that omega 2 is much higher, omega 2 is a large frequency, right. Do you see something happening between omega 1 and omega naught? Suppose this does not exist. Okay. The relationship between omega 1 and omega naught is just this minus 20 dB per decade. What does minus 20 dB per decade mean? It means that if I increase frequency some k times, then the gain is going to go down k times, right. You can write this gain going down k times in terms of decibels, but actually what it means is that if frequency goes up 10 times, that is a decade, then the gain drops 20 dB, which is 10 times, right. If frequency goes up 100 times, gain drops 100 times. If frequency goes up k times, gain is going to go down k times. So, here I have gain coming down, gain decreasing by a factor a naught. It started with a gain of a naught, ended up with a gain of 1. What is the ratio between omega naught and omega 1? It is therefore going to be equal to a naught, because gain has dropped by a naught times, therefore, frequency must have increased a naught times. So, this relationship is fine, this is okay, right, but it is also possible to say that omega 2 is a very high frequency, let us not bother about it at all, and omega naught is nothing but a naught times omega 1. It is possible to say such a thing. Okay. In which case the gain crossover frequency, the frequency at which the amplifier has a gain of 1, is nothing but a naught times omega 1. All right. Now, when you talk about bandwidth, typically if you have done any communications or filters or anything, they will say what is the 3 dB bandwidth, that is what is the frequency at which gain has dropped 3 dB. Okay. Unfortunately, in amplifier design we do not talk about that bandwidth at all. For us, the unity gain bandwidth is more important. The unity gain bandwidth is nothing but omega naught. Okay. And when you talk about bandwidth, you are just going to state the unity gain bandwidth omega naught. Unity means 1, Okay. It also happens to be the product of A naught and omega 1. This value omega naught happens to be the multiplication of A naught times omega 1. So, if you say that the 3 dB bandwidth is omega 1, that is just bandwidth, okay, and the gain is A naught, then the gain bandwidth product is omega naught. Okay. So, another way of calling it is saying the same thing, right, gain bandwidth, gain times bandwidth is omega naught. All right. So, there are many ways of calling this. So, we typically, as far as amplifier design is concerned, we typically specify the unity gain bandwidth, the frequency at which the gain drops to 1. And the reason why we do this is related to your op amp circuit. Right, which is your favorite op amp circuit? This one, this is my favorite op amp circuit. Okay. If I approximate this op amp as something which has a response that looks like this, A naught divided by 1 plus S by omega 1. Okay. It is also possible to say that omega 1 is such a small frequency that this 1 makes no difference. This could also be approximated as A naught omega 1 by S, which means that this could be approximated as omega naught by S. So, the whole op amp could be approximated as omega naught by S. All right. So, anyway, so this is the reason why. You are going to find that if you have a block like this omega naught by S, then the bandwidth is only related to omega naught. In fact, the 3 dB bandwidth of this circuit is going to be related to just omega naught and the gain of this circuit. So, we will do this in the next class. So far, this is where we stand, that we have understood how all of our techniques relate to op amp design. Okay, thank you.